In some cases, a curve may intersect more than twice. In the drawing that you can see on the screen, we actually have two curves, the purple one, y equals x cubed, and the green one, which is y equals x. Recall that even though y equals x is a line is just a special type of curve, so it's correct for me to call it that. What we can see is that these two curves actually intersect each other in 3 points, which I'll just draw in right there. And the significance of this is that when that happens, it doesn't always happen, but it can, it may happen that the curves switch which one is the top and which one is the bottom. Since we know that we find the area between curves by integrating top minus bottom, this situation actually requires you to break up the calculation into two integrals. So first thing we need to do is, in order to find the area that's bounded between these curves, and it does make sense to talk about an area bounded between curves that intersect like this. In order to find that area, we need to find the points where the two curves intersect. So we do this by setting the equations for the curves equal to each other and seeing where they intersect. And I've put up small diagrams of the same graph so you can follow along on the right. So what I would do is I'd say x cubed equals x. In other words, x cubed is the purple curve, x is the green curve, and now I do a whole bunch of algebra really fast just to solve that equation to find its solutions. So what we can see is that these two curves intersect at 3 points, 0, 1, and -1. In fact, I can just write them in here. You can see that that's where -1 is, that's 0, and that's 1. I can even write a little smaller version of that there. So those are the transitional points where we're going to have to break up the integral. So what you want to do is, instead of trying to find the entire area bounded between the curves, you want to break it up into what I've shown as the blue region on the left and the orange region on the right. So let's write out the area of the left region. Oops. In order to find that area, what we're going to have to do is we're going to have to set up the integral. We see that on the left we have -1, and on the right we have 0. In other words, there's that line, x equals -1, and this line, which is x equals 0, or just the y-axis. And then we integrate top minus bottom. We can see that x cubed is the top, and x is the bottom. So that's top, that's bottom, and then I'm going to quickly go through the algebra to find that area. So that's the area of the region on the left. Now it's your turn. You should go through the exercise of finding the area of the region on the right, and then we'll add them together. So I'll show you the calculation for the region on the right. So you can see we're integrating from the left point of 0 up to the right point of 1, and we're going to integrate the function top minus bottom. So this is going to be equal to the integral from 0 to 1 of the green is now the top and the purple is the bottom. So we're going to integrate that function. Again, here's top and here's bottom. And going through the algebra fairly quickly, we see that we actually got the same number, which shouldn't surprise you because these two regions, they certainly look symmetric. That's not always going to be the case, so the exercise is still worth it to go through, but in this case they happen to be the same. So the total area bounded between y equals x cubed and y equals x is 1/4 plus 1/4 equals 1/2. Okay, I put up an example that's a little bit more abstract. So take a look at this diagram here. I haven't actually put in what the functions are, I've just called them f and g. F is the dotted green line, and G is the solid purple line. So I'm going to ask you some questions about this region. So look at this region as the question comes up on the screen.